Okay, you guys. Well, I thought I was pausing the recording so I could just keep this all on one video, but unfortunately I didn't pause. I stopped the whole thing. So now you have to watch a second video. It's okay. I'm sure you figured it out. If you're here, you figured it out. Okay, so in this second part of our video, we're just going to do 4 more practice problems. And where were we? We were balancing this first reaction here by making our iodines equal with a coefficient of a 2 out in front. That coefficient of a 2 also made my sodiums 2, so I need a 2 out in front of my sodium on the left as well. And this reaction is now balanced. This second one, I think, is one of the ones we did in the PowerPoint, but let's just go ahead and do it again. 1 potassium on the left, 1 on the right, a chlorine on the left, and a chlorine on the right. 3 oxygens on the left and 2 on the right. Here's where we need a least common multiple because we need to make these numbers equal by adding coefficients. So I got to get to 6. So I'm going to need a 3 there and a 2 there to get my oxygens equal to 6. And by putting that 2 out in front of my potassium chlorate, now I need a 2 out in front of my potassium chloride in order to balance the potassiums and the chlorines. Let's look at the third example. 3 potassiums on the left and only 1 on the right. Pop a 3 out in front. There are 3 chlorines now on the right when I put that 3 out in front there, and only 1 chlorine on the left, so I need a 3 out in front there, which made my hydrogens 3, and on the right there 3. And all that leaves for me to check is my phosphates, so I can see my 1 phosphate unit on the right and my 1 phosphate unit on the left. Again, easier to look at those polyatomic ions as units. There's one of those things on the left, and there's one of those things on the right. And so we're balanced. Now, this last example is the one I really wanted to go over with you guys because we have oxygen appearing more than once per side. So in these reactions, these are called combustion reactions, where you have a hydrocarbon reacting with oxygen to always form carbon dioxide and water. We'll learn more about types of reactions a little later on. Anytime you see this, you're going to have oxygen here and here, and you got to remember to add them all up. And it makes your life easier to balance that element last. So let's go ahead and balance carbon first, then hydrogen, then oxygen. 3 carbons on the left. I need 3 carbons on the right. 8 oxygens, nope, that's hydrogen. 8 hydrogens on the left, only 2 on the right. So I need a 4 out there to balance my hydrogens. And now I've got a bunch of oxygen on the right. Okay, I have my oxygen from my carbon dioxide. This 3 times 2, that's 6 oxygens. Plus, and here's where you can't forget to add, that there's also 4 oxygens in the water. So really on the right-hand side, you have a total of 10 atoms of oxygen. So your coefficient over here on the left-hand side needs to be a 5. Okay, so for your combustion reactions, balance carbon, then hydrogen, and then oxygen. Makes your life a little bit easier. So putting these coefficients out in front and balancing our equation is not only important in obviously obeying the laws of nature, like the conservation of matter, but these are going to be really important in helping us determine how many or how much of each reactant do we need in order to make a certain amount of product. This is called stoichiometry, or the study of the amounts involved in chemical reactions, and we're going to get to this. And if you think about the real world consequences of that, if they come up with, a treatment for COVID-19 or a vaccine, those things have to be manufactured, and they're going to have to be manufactured on a massive scale. And so when you want to start manufacturing something, you need to do the backwards math to figure out, okay, well, if I need, 350 million vials of this vaccine, how much of reactant A, B, and C do I need in order to create that much product? Same thing with like baking. We do it every day in our kitchens. If I want to make, a loaf of bread, how much sugar, how much flour, how many eggs do I need? These are the recipes for chemical reactions. And of course, we're using these chemical reactions not just to make medicines and to create the stabilizing compounds we need for vaccines, but also for, producing materials to build things with. So you'll find these kinds of calculations anywhere from your biochemistry classes to your engineering classes to your molecular gastronomy classes when you guys go to chef school. So you've got plenty to practice with, and I will see you in class.